in this lecture, we're going to talk about types of collisions. Objects in an isolated system can interact with each other in two basic ways. They can collide, and if they get stuck together, they can also explode or push apart from one another. In an isolated system, both momentum and total energy are conserved, but the energy can change from one form to another. Conservation of momentum and changing kinetic energy can help us predict what will happen in these events. We differentiate collisions and explosions by the way the energy changes or does not change form. So for instance, in inelastic collisions, two objects collide, converting some kinetic energy into other forms of energy, such as potential energy, heat, or sound, or even light. Elastic collisions are when two objects collide and bounce off each other while conserving kinetic energy. Energy is not transformed in any other type. We can also have explosions. An object or objects break apart because potential energy stored in one or more of the objects is transformed into kinetic energy. There are two types of inelastic collisions. Perfect inelastic collisions, in which two objects collide, stick together, and move as one object after the collision, transferring kinetic energy into other forms of energy, and general inelastic collisions, in which two objects collide and bounce off each other, transferring kinetic energy into other forms of energy, such as light and sound and heat. There is really no such thing as a perfect elastic collision. During all collisions, some kinetic energy is always transformed into other forms of energy. But some collisions transform so little energy away from the kinetic energy that they can be dealt with as perfect elastic collisions. In chemistry, the collisions between molecules and atoms are modeled as perfect elastic collisions to derive the ideal gas law. Other examples include a steel ball bearing dropping on a steel plate, a rubber superball bouncing on the ground, and billiard balls bouncing off of each other. A firecracker is an example of an explosion. The chemical potential energy inside the firecracker is transformed into kinetic energy, light, and sound. A cart with a compressed spring is also a good example. When the spring is against a wall and it is released, the cart starts moving, converting the elastic potential energy from the spring into kinetic energy and sound. Think for a moment. Can you see a resemblance between this phenomena and either an elastic or inelastic collision? In both an inelastic and an explosion, kinetic energy is transformed into other forms of energy, such as potential energy, but they are time reversed. An inelastic collision transforms kinetic energy into other forms of energy, such as potential energy. An explosion changes potential energy into kinetic energy. Thus, the equations to predict their motion will be inverted. The next slide summarizes the four types of collisions and explosions. Okay, so let's say the event is a general inelastic collision. The description would be objects bounce off each other. Is momentum conserved? Yes. Is kinetic energy conserved? No. Kinetic energy is converted to other forms of energy in this case. What if we had a perfect inelastic collision? Well, in this case, the objects stick together. Is then a momentum conserved? Yes. What about energy? No. Kinetic energy is converted to another form of energy. How about elastic collisions? Well, this is when the objects bounce off of each other. It's very similar to general inelastic collisions. Is momentum conserved? Yes. Is energy conserved? Yes. Explosions. Again, remember, this is the reverse of an inelastic collision. This is when an object or objects break apart into many pieces. Is momentum conserved? Yes. Is energy conserved? No. You're releasing potential energy, and that increases the kinetic energy. Notice here from this list that the only type of collision in which energy and momentum are conserved are going to be your elastic collisions. In blank collisions, momentum is conserved. Is it A, elastic, B, inelastic, or C, both? Pause the video now. Okay, let's see if you got the right answer. The answer is C. Momentum, remember, is always conserved, no matter what type of collision you have. In blank collisions, kinetic energy is conserved. Is it A, elastic, B, inelastic, C, both? Pause the video now. Okay, let's see if you chose the right answer. Did you choose A? That would be the correct answer. In an inelastic collision, kinetic energy is transformed into what after the collision? There's two correct answers. Is it nothing? Kinetic energy is conserved. Is it more kinetic energy for B? Is it C, thermal energy? How about D, light energy? Pause now. Okay, let's see if you chose the correct answers. The correct answers are C and D. It becomes thermal energy or light energy. Now we're going to talk about conservation of momentum with collisions. During a collision or an explosion, measurements show that the total momentum of closed system does not change. The diagram below shows the objects approaching, colliding, and then separating. So here you can see the two objects are moving towards one another. Then they collide right here. And then after the collision, you can see that they move off. Okay. When we write this equation out, we're going to write out the momentum that we start with, which is right here. And that's got to be equal to the momentum that we end with, which is right here. The prime tells us, right here, that it's after the collision. Okay. There is something missing, and I'm going to add them right now, so please add them to your lecture notes. Remember that the velocity is a vector quantity, and we need to make sure we keep in mind that we need that. I'm going to also add it to our drawings so we can make sure that we are using the correct notation throughout. If the measurements don't show that the momentum is conserved, then this would not be a valid law. So fortunately for us, it is a valid law, and these things do work out correctly. In a perfect inelastic collision, two objects will collide and stick together, and then they move afterwards as one single object. So here the momentum for A is going to be equal to mVA. The momentum of B is going to be mBVB. After the collision, notice that the total momenta of both of them is equal to the total mass times their final velocity, because they stick together. So here we have the momentum that we start with, and that's equal to the momentum we end with. Because they have the same velocity, because they stick together, we can just add the two masses together here. Okay, so let's do an example. I'm going to go ahead and make corrections to the example as it's shown. So I want you to go ahead and solve the problem first, and then I'm going to go ahead and show you the answer. A 13,500 kilogram railroad freight car travels on a level track at a speed of 4.5 meters per second. It collides and couples with a 25,000 kilogram second car, initially at rest, with brakes released. No external forces act on the system. What is the speed of the two cars after colliding? Well, let me just start off by saying we have a bit of a problem. We can't use speed in momentum equations because it's a vector quantity. So I'm going to replace this with velocity. And you'll have to excuse me, I am writing with my fingers on the mouse pad. Okay, so we're going to ask for what is the velocity afterwards. We could answer this question and give the speed, but I'm just going to go ahead and change both of these to velocity. Okay, we're going to assume also that this is going in the I-hat direction or going east. Okay, so go ahead and solve the problem now. Okay, let's check your answer and see if you have the right answer. We know that M1 is 13,500 kilograms, M2 is 25,000 kilograms. I need to fix this a little bit. Okay, so my initial velocity for car 1 is going to be 4.5 meters per second I hat. For car 2, it's at rest at 0 meters per second I hat. And I know that V prime is the same as V2 prime and the same as V1 prime because they're connected together after the collision. So starting with the momentum of both objects, we end up with M1V1 plus M2V2. And that's equal to the momenta of both of the cars after the collision. Again, we know that the momenta is the same, or I'm sorry, the velocity is the same for both cars. Solving for that final velocity, we end up with M1V1 divided by the sum of the masses. Substituting in from our from our equation or given information, we end up with 1.6 meters per second I hat. So it's going to be in the same direction as our initial velocity of the first vehicle. Notice, though, that this is much slower, and that's because you're taking an object that's less massive with a higher velocity, and you're combining the mass of that and the second car. That increases the mass, and that means we have to decrease the velocity in order for the two sides of the equation to be balanced or for momentum to be conserved. A cannonball with a mass of 100.0 kilograms flies in horizontal direction with a speed of 250 meters per second and strikes a ship initially at rest. The mass of the ship is 15,000 kilograms. Find the speed of the ship after the ball becomes embedded in it. Again, we're going to make some changes here. I'm going to go ahead and give this a direction of I hat, and I'm going to call this the velocity, and to make it easier for me and you, I'm just going to put a V with a vector sign. And again, instead of finding the speed, I want to find V final, or V prime, of the ship. Okay, so go ahead and pause the video and see if you can solve for the answer. Okay, so let's go ahead and check and see if you got the right answer. We know the mass of the cannonball is 100 kilograms. The mass of the ship is 15,000 kilograms. Our initial velocity of the cannonball is going to be 800 meters per second I hat. We know the velocity of the ship is 0. It's not moving. We also know that the ship and the cannonball both join together after the collision, and therefore the final velocity of both is the same value for both. We're going to add up the momenta before the collision, which is the momenta of the ball, which is right here, plus the momentum of the ship, and that's equal to the momentum after the collision of the ball, plus the momenta after the collision of the ship. We know that the momenta of the ship is 0, and we know that the velocity of the boat and the cannonball must be the same since they're joined together. Solving for the momenta of both after the collision, we end up with M1V1 divided by M1 plus M2. Substituting in from our given information, we're going to have 100 kilograms times 250 meters per second. Actually, that should be, is that 200 or 800? Okay, let's change this. This should be here. That should be 250. Okay, sorry for that confusion. Okay, so we have 100 kilograms times 250 meters per second I hat divided by the 100 kilograms plus the 15,000 kilograms, and that should give us 1.7 meters per second I hat. Okay, so that tells us how fast and the direction for the cannonball and shift after they collide. Okay, next example. A 40-kilogram girl skates at 5.5 meters per second on ice toward her 70-kilogram friend who is standing still with open arms. As they collide and hold each other, what is their speed after the collision? Again, we're going to change this to, what is V prime with a vector sign? Okay, go ahead and we'll assume, okay here, we'll assume that the girl is going at 5.5 meters per second I hat. Okay, go ahead and pause the video and solve the problem. Okay, let's see if you got this one right. Let me change to my selector thing. Okay, so we have the mass of the first girl is for 40 kilograms. The mass of her friend is 70 kilograms. Her initial velocity is going to be 5.5 meters per second. The initial velocity of the friend is 0 meters per second. And we know after the collision they are joined together and that they all have the same final velocity. Again, the momentum we start with is equal to the momentum at the end after the collision. Solving for the velocity of both of them after the collision, we get the same exact equation we have in the last two examples. Substituting in our numbers, we end up with 2 meters per second I hat. If you have any questions with any of these problems, go ahead and leave a note for me on Edmodo. Okay, in the next video, I'm going to go ahead and start with explosions.